Back in the early 19th century, Madelung and Born laid out the foundation of the classical theory of ionic crystals. Experimentally, it is found that the specific heat of practically all simple solids approaches zero as the temperature goes to absolute zero. This fact cannot be explained on the foundation that Madelung and Born set out, and instead we look towards Einstein to give a qualitative interpretation on the basis of quantum theory. Einstein assumed that a simple crystal could be regarded as a lattice of atomic oscillators, each of which vibrating at the same natural frequency. You can think of this as a bunch of positively charged spheres connected by springs. In addition to this, he assumed that the allowed energy states of these oscillators were integer multiples of the frequency of oscillation and Planck's constant. A few years later, Debye improved on Einstein's theory by a more accurate analysis of the modes of vibrations in a simple solid. Instead of having each move at the same natural frequency, Debye suggested that a more accurate description might be found by treating the crystal as though it were a continuous elastic medium, which has elastic constants that are independent of frequency. What we are going to do now is find the modes of vibration of a one-dimensional lattice to show that this assumption that Debye made is incorrect. This actually generalizes to 3 dimensions, but the concepts and ideas are the same. There just happens to be a lot more algebra involved. Alright, so the first thing we're going to assume is that the atoms are equally spaced a distance a apart. We're also going to assume that the interaction between the atoms obey Hooke's law. The reason why we assume this is for simplicity. This assumption turns out to not be completely true, but for the purpose of what we're doing, it is perfectly fine. Now, since we're inside a solid, we're usually dealing with upwards to 10 to the 23rd atoms. Because this number is so large, we're going to assume what's called Born-von Karman boundary conditions. That is to say, instead of having n atoms in our lattice, we're going to allow our lattice to be infinitely long. The way we do this is we take our original n lattice and copy and paste it over and over again. Next, we're going to assume that the phase that the first atom is in our n lattice, is the same as the first atom in the copy lattice. We call this the periodic boundary condition, and we use it because it allows us to find the solutions without having to deal with an infinite string. And additionally, it takes into account the proper number of degrees of freedom that the system has. A degree of freedom is the number of values in a calculation that has the freedom to vary. So in our case, we would assume, because we have n atoms connected by n-1 springs, to have n-1 degrees of freedom. Lastly, we're going to assume that the equations of motion for the nth atom is going to be in the form of a wave, given by this equation. A is the amplitude, this n is the number of atoms in our lattice, this nu is the frequency, t is the time, this n is the index of our atom we're looking at, and lastly, this L is an unknown integer. Alright, now let's analyze the forces on the nth atom. As we can see, we have the force from the n+1th atom here, and this force obeys Hooke's law by assumption. And from the left, we also have a force from the n-1th atom, which also obeys Hooke's law. We're going to assume that the Hooke's constant for both of these springs are the same. So overall, we get the sum of the forces on this atom is the first force plus the second force, as shown here. And we can relate these to the acceleration of the nth atom by Newton's second law, which states that the sum of all forces on a particle is equal to its mass times its acceleration. And acceleration is just given by the second time derivative of the position. Putting these together, we get the following equation. And from this equation, as they both have the same Hooke's constant, we can factor that out of the two terms. Now remember how we assumed that the solution are in the form of a wave? We're going to substitute that solution into this equation here for each of the particles. Looking at the left-hand side first, we're going to take the second derivative of the wave, which will give us this solution. Putting this back into our original equation, notice how we have e to the 2 pi I L over big N times N minus mu t in every term. So we can factor out that from every term, and then divide both sides, and this will leave us with this equation here. Now we're going to utilize what's called Euler's identity. This is e to the I theta is equal to cosine of theta plus I sine theta, and gives a bridge to connect the exponential functions and the trigonometric functions. Using this identity, we can replace our remaining e's with cosines and sines as given here. Now notice how the cosine and sines are even and odd functions. This means we can take the minus sign and pull it out of the sine functions, and the minus signs become plus signs in the cosine functions, as here. This leaves us with this equation here, which we're going to solve for the square of the frequency. And to pretty this up, we're going to use a power reduction trig formula. Recall that 1 minus cosine of 2 theta over 2 is going to be equal to sine squared of theta. So using this and taking the square root, we find a function for frequency. From this, we can find the modes of the system. These are going to be the integers L that give a unique value for our frequency. That means that L is going to be an integer that ranges from 0 to n minus 1, where n is the number of atoms we started with. It is convenient to solve these expressions in terms of what's called the wave number. The wave number is defined as 1 over the wavelength. And the wavelength here is going to be the number of atoms we have times the spacing between them over the mode. So the wave number is the number of waves per unit distance. So we can now represent our frequency function in terms of the wave number. If we plot the frequency versus wave number, we'll get this curve that looks kind of like a bird. If the assumptions made by Debye were to be true, then the curve we see here should be linear. However, that's not what we see here. Instead, we see that the velocity of the wave is dependent on frequency, as we can relate the two by this expression here. So what gives? Groneisen and Goons first suggested that the difference should be explained on the basis of differences between the velocity in short and long waves. The fact that short waves travel more slowly in this lattice suggests that we should use elastic constants that are somewhat smaller than obtained from ordinary measurements. Blackman has investigated this further, but we're not going to get to that today.